Hello everyone and welcome to the video for section 9.5 on the alternating series. The objectives for this video are: number one, use the alternating series test to determine whether an infinite series converges. Number two, use the alternating series remainder to approximate the sum of an alternating series. Number three, classify a convergent series as absolutely or conditionally convergent. And number four, rearrange an infinite sum to obtain a different sum. Now let's look at what is meant by an alternating series. Okay, really what's happening on this thing in the previous sections, everything we've dealt with has been positive. All the terms were positive. With an alternating series, what you're going to see is literally the series is going to alternate between positive and negative terms. So examples of these would be one like negative 1/2 to the n, which would be 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1 over 32. And then this one right here, where we have negative 1 to the n plus 1 over n plus 3, and it would go and extend like that. These would be examples of alternating series. And again, remember, you do have positive and negative terms in this. So when we look at the alternating series test for convergence, one of the things that you have is we're going to let a sub n be positive. So really what we're looking at here, you'll notice the alternating series is negative 1 to the n or negative 1 to the n plus 1, both times a sub n. So these are alternating series. When a sub n is positive, this is going to converge when the following two conditions are met. Number one, the limit as n approaches infinity of a sub n has to go to 0. And number two, a sub n plus 1 is less than a sub n for all n. Okay, now this part right here is where we start getting into a little bit of confusion on this one. And the reason, because it looks very much like the nth term test. And we said when the limit of the terms goes to 0, that didn't necessarily mean that the series converged. Well, that's true. And that's still actually true here because you still have to meet that other condition. But the other thing that happened with that nth term test, we were looking at things where they were always positive. Okay? So that's why this one works out this way. So let's look at a couple examples. So on this problem, this first problem that we have, n is going from 1 to infinity of negative 1 to the n over e to the n. So in this case, a sub n is 1 over e to the n. And so when I take a look at that one, I'm going to start out, I can say that the limit as n approaches infinity of 1 over e to the n is going to be 1 over, basically go off to 1 over infinity, which is 0. So it meets that condition. And the other thing that we have is that when I take a look, 1 over e to the n plus 1 needs to be less than 1 over e to the n. Well, in this case, as you know, because our numerators are staying the same, our denominators are getting bigger, that's always going to be the case. So therefore, we can say that this series here converges by the alternating series test. Now let's take a look at this next one. In this case, what we're looking at is we have the series n equals 1 to infinity of negative 1 to the n plus 1 over the natural log of n plus 1 over n plus 1. So again, a sub n is natural log of n plus 1 over n plus 1. So to start out with, I want to go through and determine if this thing is, I want to show this one converges by the alternating series test. And so what I'm going to do is I'm going to start out by taking the limit as n approaches infinity of the natural log of n plus 1 over n plus 1, which that's going to end up being infinity over infinity, which in determinant form. So I know this is going to equal the limit as n approaches infinity of the derivative of the top, which will be 1 over n plus 1, over the derivative of the bottom, which is 1. And as n goes to infinity, that's going to be 0 over 1 or 0. So therefore, the first condition is met. The next one I have to look at is this thing has to be decreasing. The terms have to be decreasing. So and this one's a little bit harder to do. The first one I could do very quickly by looking at it and realizing that my denominators were getting bigger while the numerator was staying the same. That's clearly not going to be the case in this problem because my numerator is changing too. So to show that the terms are decreasing, what I can do in this case is I can go and take the derivative. So if I take the derivative of that, I'm going to have to use the quotient rule. So when I take the derivative, I'm going to get the derivative top 1 over n plus 1 times n plus 1 minus the derivative of the top, the natural log of n plus 1 times 1, the derivative of the bottom, all over that bottom squared. So that this thing is going to simplify to be 1 minus the natural log of n plus 1 all over n plus 1 squared. Now this thing is going to be, we have to show that this is going to be negative for n greater than 1. Well, here's the thing. When n greater than or equal to 1. So in this case here, the issue is going to come in. The denominator is always going to be positive, so that's not an issue. The issue is the numerator. And so when n equals 1, I'm going to get the natural log of 2. The natural log of 2 is a value that is bigger than 1. So therefore, I know the numerator is going to be negative. And therefore, so that we know that this, that my derivative here will be less than 0 for n greater than or equal to 1. And so therefore the terms are decreasing. So by the alternating series test, I know that this series here is converging. Now, take a minute, pause the video, make sure you're comfortable with all the calculations that we did on this one, and once you are, we'll move on. Here's another alternating series, and this one's a little bit different in that we don't, in terms of it, we don't have like a nice easy general rule I can work with, okay? I have this series here that negative 1 to the n plus 1 times this. So a sub n is this. So what you're going to see here, it's 1, 3, 5, so we're just getting all the product of the odd integers there. And then 1, 4, 7. So we're always going up by 3. We're taking the product of those integers as well. And so what we want to do on this one is we need to go through and show that the conditions for the alternating series test are working. So what I'm going to do on this is what you have to keep in mind is we do have the same number of factors in the numerator and denominator. Okay, so we're going to rewrite this in a way to go through, and we're going to pull out different factors to kind of make this thing a little bit easier to work with. So the first thing I'm going to do is I have this here, but what I'm going to do is I'm going to take the 3 and the 1, and I'm going to pull those out. So I'm going to have 3 over 1 times everything else. Okay? And now we're going to take this 1 and we're going to move it to the end. So I have 3 over 1 times 5 times 7 times times the 2n minus 1 times the 1, and then we have the 4 times 7 times all the way down to the 3n minus 2. Okay, so notice, all we've done, we've pulled out 2 factors. We had the same number of factors here in the top and bottom. We pulled out 1 from the top, 1 from the bottom, so we still have the same number of factors there. And I've rearranged them here. And now I'm going to take these 2 and I'm going to pull them out. So I'm going to have the 3 over 1 or 3 times, and then that's going to be, I'm going to put all these over their thing. So 4 over 4 times 7 over 7 times 9 over 10 times times the 2n minus 1 over 3n minus 5, because it's these 2 there. And then I have the times the 1 over the 3n minus 2, which are the last 2 factors there. Okay. And so, in this case, the limit as n approaches infinity of this is going to be the limit as n approaches infinity of this whole expression, which that whole expression is going to, the thing you have to recognize on this is that as n gets larger, we're going to be multiplying by fractions here, but the fractions are going to be approaching 2/3 as n gets larger and larger, because that would be the horizontal asymptote there. So I have 3 times all these things here, which would go to 2/3, times 1 over the 3n minus 2. Well, as n goes to infinity, that's 0. So I get a constant. This is all, while yes, we do have the n's, and this is going to be, you have to keep in mind that these values are going towards a constant value. So this is going to be constant as well, times 0. So in this case, I know that this particular problem, that is going to be 0. So therefore, we know the terms go to 0. The next thing I have to look at is what's happening. Do the terms get smaller? Well, in this situation here, a sub n plus 1, here's a sub n, and then a sub n plus 1 is going to add on these 2 factors here. That factor in the numerator, that factor in the denominator. And so what happens, because remember, we're putting n plus 1 in for n, so 2 times n plus 1 minus 1 will be 2n plus 2 minus 1. That's what gives us this. And the same idea here. We're replacing the n here with n plus 1. But the end result is that this is going to be a sub n times this. And again, as n goes to infinity, this is going to 2/3. Therefore, this is always less than 1. So therefore, a sub n times this will always be less than a sub n. So that will be less than a sub n, and therefore we can say that this series up here converges by the alternating series test. Again, pause the video right here, make sure you're comfortable with the calculations that we did, and once you are, we can move on. Now, one of the nice things about the alternating series is the fact that the partial sums, it's very easy to go and calculate the error that is associated with it. Remember, when we're working with a series, infinite series, we can approximate that infinite series by finding the partial sum. And so what we have in this is that the actual sum of the series minus that partial sum, that if you take the absolute value of that is the amount of error that we have, and that's r sub n, okay? That's the remainder, okay? Now, if a convergent alternating series satisfies the conditions that a sub n plus 1 is less than a sub n, okay, then the absolute value of the remainder involved in approximating the sum s by s sub n is less than or equal to the first neglected term. In other words, if I find the sum if I approximate the sum of an alternating series using the first 5 terms, the error is going to be less than or equal to the 6th term. Okay, and that's what this is saying, that error is always going to be less than or equal to, that right there is the next term. So whichever one you stop with, you go through, take a look at that next term, that's going to be the error. So for example, let's say I have the alternating series -1/2 to the n power, n equals 1 to infinity. So this series is going to be equal to -1/2 plus 1/4 minus 1/8 plus 1/16, and so forth. So in this case, S sub 3 is going to come out, if I went through and took that, it's going to be -1/2 plus 1/4 minus 1/8. And when I do that, that's going to be negative 3/8. Okay, so what we have on this one is I know that negative 3/8, that is my approximation of this sum. And I know then that the next term by this theorem, by this alternating series remainder theorem, I know that my error is going to be, the absolute value of my error is going to be less than 1/16. So I know that the true value of this sum is going to be between negative 3/8 minus 1/16 and negative 3/8 plus 1/16. That will give me the true value of this particular alternating series. Now another example that we have is where we're going to go through and use this remainder theorem to help us identify how many terms we have to use to get to where our error is, that we are within a certain amount that we have. So in this case, I want to find the number of terms needed to approximate the sum of a series so that the error is less than 0.001, which is 1 over 1,000. So my series in this case is negative 1 to the n over n squared. So a sub n is 1 over n squared. By our remainder theorem, I know that the absolute value of the remainder is going to be less than or equal to the next term, which the next term in this case is n plus 1, that 1 over n plus 1, that quantity squared, and I want that less than 0.001. So I can say 1 over n plus 1 squared has to be less than 1 over 1,000. So from that, I can say that n plus 1 squared has to be greater than 1,000. And now I can just take the square root. And when I do that, I get that n plus 1 has to be greater than 31.62. And so n will have to be greater than 30.62. So in order to get the required, to be within the required amount of error, I know n needs to be 31 terms. Okay. Now, the other thing that's going to happen here is that we are going to start looking at types of convergence. That series that can be, there are series that will converge, that they have absolute convergence versus conditional convergence. Okay. And what's happening here, when we talk about this, we're looking again at series that have positive and negative terms. So when I look at this first example here, I have n equals 1 to infinity of sine n over n squared. Okay. This is not an alternating series, because sine of n doesn't just alternate between 1 and negative 1, okay? Positive and negative numbers. It's going to change. Sometimes you could have a couple positive, a couple negative. So it does. This one right here does not follow with the alternating series test. We can't use the alternating series test to show that this thing converges or doesn't converge. Also, because sine of n can be negative, all those other sequences, all those other tests that we've used so far doesn't help us out. But one of the things we have is that we can go on this one and I can take a look at the series 1 to infinity of the absolute value of sine n over n squared. Now, why is that helpful? Well, because when we're looking at that, the sine of n, while it isn't, it alternates, it changes, it doesn't alternate, it changes sometimes between positive and negative values. We do know it's bounded. And therefore, I know that this series right here is going to be less than the series n equals 1 to infinity of 1 over n squared, which is a convergent p-series. And so therefore, because I know this converges, I know this converges. And so what we have here is our first definition that we have. We have what's called absolute convergence. And what that says is this. If the series of the absolute value of a sub n, if that converges, then the series of A sub n converges. Absolutely. The issue with this is it doesn't always work. For example, when I look at this particular series right here, -1 to the n over n, this is an alternating series. But if I looked at the absolute value of that series, that would be 1 over n, which we know this series diverges because that's the harmonic series. But by the alternating series test, I can say that this series is going to converge. So the other thing we have is what's called conditional convergence, okay? And what that says is this: if the series A sub n converges, but the series where the absolute value of A sub n diverges, then we say that that series A sub n converges conditionally. Okay, so those are the two that you're going to have. So now, instead of asking you if it converges or diverges, they're going to ask you the type of convergence as well. Does it converge absolutely? Does it have conditional convergence? Now, one of the consequences of conditional convergence, if you have absolute convergence, if a series converges absolutely, then the sum it converges to is the sum. It's not an issue. But conditional convergence has a interesting property in that when you have conditional convergence, its terms, a lot of times its terms can be rearranged and could give you a different sum. And so what we're going to look at here is the harmonic series, the alternating harmonic series here, -1 to the n plus 1 over n. Now, later on in this chapter, we are going to go through and show you that this series here will converge to the natural log of 2. Okay? We're going to show that. But for right now, we'll just accept it. And so if I write out an expansion here, and you'll notice I took a lot of terms here, that is the plus the dot, that's going to equal the natural log of 2. And so what I'm doing here is I'm grouping terms together and rearranging them. So 1 minus 1/2. I'm really taking the odd, what would have the odd denominators. I'm moving them and pairing them up with the fraction that they would be half of, or that would be double them. So 1 minus 1/2 minus the 1/4. I move the 1/3 with the 1/6. I move the 1/5 with the 1/10. I'm going to move the 1/9 with the 1/18, and so forth. Got the 1/7 with the 1/14, so forth. And so I have this. Okay. And again, the 1/9 is going to be further down, the 1/11 further down, 1/13 further down too. So I'm going to get this, and what the end result is, I'm going to get 1/2. 1 minus 1/2 is 1/2, minus 1/4, plus 1/6, minus 1/8, plus 1/10, minus 1/12, plus 1/14. So you can see the pattern that's happening. Okay. Now, what's going to end up happening then with this is I can take this and I can pull out my common factor. I can pull the 1/2 out. So when I pull the 1/2 out, I'll get 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 and so forth. Well, this in green is the same as what we had in black up here. And so I know this in green is also equal to the natural log of 2. So this expression here will be 1/2 times the natural log of 2, just by rearranging those. And again, that is a consequence of conditional convergence. Okay? Yes, what's it equal to, this or that? The answer is yes, both. So with that, this does conclude this video. dealing with the alternating series test and absolute and conditional convergence. Make sure you're comfortable with those definitions, and we will see you in class.